Welcome to the DDPS seminar, everyone. Before we introduce our invited speaker, let's go over some rules as usual. First of all, please mute yourself during the talk. If you have immediate questions, you are welcome to unmute and ask, or otherwise, please use the chat room to post your questions so that we can address them in the Q&A session at the end. Second, today's seminar is open to external audience, so no classified discussion is allowed. Finally, the talk will be recorded and uploaded to our YouTube channel. Now, let me introduce our speaker. It is an honor to host Christopher Vakukas, who is the Vice President of Modeling and Simulation at Julia Hub, the Director of Scientific Research at Pumas AI, co-PI of the Julia Hub at MIT, and the lead developer of the SciML open source software organization. For his work in mechanistic machine learning, his work is credited for the 15,000 times speed up of NASA launch surfaces simulations and recently demonstrated a 60 times to 570 times acceleration over molecular tools in HVAC simulation, and increased the U.S. Air Force Artificial Intelligence Accelerator Scientific Excellence Award. He is the lead developer of the Pumas project and has received a top presentation award at every ACOP in the last 3 years for improving methods for uncertainty quantification, ultimate GPU acceleration of nonlinear mixed effects modeling, and machine learning assist construction of the NLME models with deep NLME. For these achievements, Chris received the Emerging Scientist Award from ISOP. Today, he will talk about generalizing scientific machine learning and differentiable simulation beyond continuous models. Please enjoy the wonderful talk. Now, with no further ado, let me hand it over to Christopher.
Yeah, thank you. I mean, I'll jump right into this. Thank you for the nice introduction. So what I want to talk about today is scientific machine learning, right? And what scientific machine learning is I think that this seminar, everyone's kind of familiar with it. But the core idea behind scientific machine learning is that you have this information in your scientific models that you don't necessarily have in your data. So for example, with general relativity, there is no data set that, kind of captures, what general relativity is, right? There is no 3 billion line website that, like what Google has for general relativity. There are thousands of experiments that have shown us that it's true. There isn't that data set, right? So if we want to build these AI systems that are, correct and predictive, what we want to do is we want to be able to use that knowledge as though we had data without having to require that we just go out there and gather that data, right? So how do we do that? How do we build a machine learning kind of system that is incorporating all of the knowledge that we know and using that as a starting point, and then using our data to then go beyond the pieces that we know? This is what we're doing with scientific machine learning. And the core point of what I want to hit on here is that differentiable simulation is a very specific way of doing scientific machine learning. And I want to talk about how differential simulation is hard, but it's worth developing more time in, right? So, I want to really develop what differentiable simulation is, why it's important, why it's a hard way of doing scientific machine learning, but why it has a lot of payoff. And so first of all, what is our approach to scientific machine learning? A lot of what I'll be talking about today will be in this realm of these universal approximator differential equations, also kind of shorthanded to universal differential equations. The core idea behind them is it's a very general object where you say, I have differential equations which are defined in part by universal approximators. So what's a universal approximator? A universal approximator is any kind of object that is a representative of space of functions from Rn to Rm. So a neural network is your classic example, where there is the universal approximator theorem, which says that for sufficiently large neural network, so sufficiently large in terms of the size of the hidden layers or the number of hidden layers, then with the sufficiently large neural network, you can approximate any possible function. You can find weights of the neural network such that its inputs go out to the output, such that over the whole, over a whole domain omega, f of x is a neural network of x is approximately f of x for all, x in there within some epsilon, right? There's a way to be able to formalize this property that, a sufficiently large neural network can approximate any possible function that's sufficiently large. The reason why neural networks are used for a lot of these cases is because they overcome curse to dimensionality. So for sufficiently large dimensions, they might be a nice object to do this, but it's not the only object that we use here. You can also make use of polynomial chaos expansions. You can make use of, Legendre expansions. You can use Fourier series. All of these things are function approximators. Now, a lot of them are designed in 1D, and so if you use a tensor product approach to build up these function approximators like a Fourier series into higher dimensions, you have exponential growth in the number of terms. This is the curse of dimensionality. And so in some cases, we use some things that overcome curse of dimensionality, other cases you don't. But the core idea here is that you have function approximators. You have things that can stand in for functions that you don't know. And what you do is you build models that make use of all of this information you know. So here, for example, is a version of Loc-Volterra. So we have a version of Loc-Volterra where we say, x is the number of bunnies, and if I leave bunnies alone, I get exponentially more bunnies. And if I leave wolves alone, I get exponentially less wolves over time. And there's something more to this model that I don't know. There's something extra, and whatever this extra thing is, it's who knows? It's something that happens when we put rabbits and wolves together, but they never teach you that in elementary school for some reason. So what happens when we put rabbits and wolves together? That's what this model is saying. And so what we then do is we train this this model. We train this neural network, this function approximator, to capture the thing that we did not know how to model, right? And so that's step one, right? So once you do that, you then have a computational representation of the thing that you did not know how to model, right? So you don't necessarily know what it is, but you have a computational object that is able to do input-output relationships such that the thing that you did not know how to model is correctly chosen to now match the data. So once it's trained, it becomes a function it becomes an approximation to the function that you did not otherwise know how to write down, right? And now what can you do with that? Well, you can do all sorts of analyses, right? You can say, understand the sensitivities of the piece of the model that you did not know. You can find its Jacobian. You can do all these things that you would want to do with a model just on the thing that you previously did not know how to model. And one of the things that we then commonly do is we perform a symbolic regression, right? We say, well, now that we've learned in such a way that we've made use of all of our prior information, let's now try to understand that model element in terms of some more primitive pieces, some pieces that are representative of mechanistic portions, which if we were to write a model ourselves, we would use these pieces, right? And so you can then do this kind of symbolic regression process and have it spit out equations which are more readable, and they actually tend to improve the generalizability of the approach as well. So to really kind of understand this entire approach, I want to kind of walk through this step by step. So here we start with just standard machine learning, right? So the standard machine learning approach here that we're just going to do is a neural ODE, right? Just pure machine learning. U prime equals a neural network, right? So we're saying learn any possible function such that I've represented this time series. I go from 0 to 21 days worth of data, right? So I just learn from 0 to 21 days, just that many data points. I fit the model and I extrapolate forward. And this is the first data from the first 21 days in the Wuhan region of China from the COVID-19 outbreak. And now you look at this and you go, well, the lines for the estimated from the model are completely not fitting the data at all after the training regime, right? And that you are right. This is what happens with machine learning, right? Machine learning does not necessarily extrapolate well to outside of its data set. So what I'm saying here is that we have a lot of prior information, though. Like I told you that this is an epidemic model, and so when you look at this, you go, well, of course, that's the start of an exponential growth, right? But the machine learning model does not know that information, right? We just told the machine learning model, hey, here's a bit of data from the start of a pandemic, go for it, right? It doesn't even know what a pandemic is. It just is fitting the data and it's just extrapolating forward. So what happens if we tell it a little bit about what a pandemic is? So here now we have this form of a universal ODE. So so this is a version of one of these epidemic models where we now have a susceptible individuals, that's S. We have the susceptible individuals become exposed. The exposed individuals become infected. Over time, they either recover or they die, right? So this is the SEIRD model. Now, one of the interesting things that happens when we go to this kind of mechanistic model form is that we now can use heterogeneous data and prior information inside of this process, right? So, for example, we can know a lot of the details about some of the ratios between some of the reaction rates in this model because they can be directly estimated from what percentage of people die versus recover, right? So we don't need to actually use our time series to get a lot of these values. We can use prior information to be able to say, well, the percentage of folks who died from this disease is mu, and so you can start to write down these values directly from other sources of information, right? So now we're bringing in other information in a scientific way. We're using all the knowledge that we have, but the piece that I want to highlight here is that when we're talking about something like COVID-19 exposure, that was very dependent on the region of the world that you were in, right? So for example, if you're in China versus if you're in Sweden versus if you're in Italy versus which state of the United States you're in, there are completely different exposure patterns to the virus. And so writing down a simple equation for how exposure to COVID-19 occurred is not necessarily easy to do. But what we can do is we can say, well, we know a lot about this model, but the piece that we don't know how to model is the exposure term. So let's just make that one exposure term be our neural network, the function that we did not know how to model. Let's put a neural network right there. And now we have all the prior information we have. We have a machine learning model extending it. And then from that, we're able to then see if it's just 0 to 21 days worth of data, we extrapolate forward, and we can extrapolate much better, right? We're able to get about 20 days of extrapolation, right? And so the key here is that we're using a lot of other prior information. It's like we're not gaining something for free. We are putting more into the system and getting more out of it. But there's other more concrete ways to also be able to understand this. So if our neural network is always outputting a positive value, so we just make the last layer be a square function or an absolute value, then what we know is just looking at the equations is that S prime is always negative. And so just from this information, we can actually infer a lot of things. So what we have is a model that starts with an exponential growth phase, and then E will go up, and then it'll have a peak and go down. So we'll have a single peak. And so you can think about this as now, the world of machine learning was about function approximators, right? That's where I started. But by design, what I've done now is I said, here is a form for universal function approximation where it is functions which have to start with an exponential growth phase and then have a single peak, right? So essentially encoding the types of properties that we know to be true with epidemic type models. And so, that's, there's different ways to think about it, that like, hey, I made this model as epidemicness as possible, that's more high level, but also mathematically, I've restricted the function space that I'm allowed to be fitting functions of. And so from the same amount of data, if my true function is supposed to be living in this function space, which I've restricted to, then what I've done is I just made it so that way I more easily can be finding the right function because I'm finding a function from a subset of the larger set of all possible functions, right? Now, the last stage of this universal differential equation process is to do the post analysis. So this is always an interesting step. So what we do here is we say, well, we've trained this neural network in such a way where it captures all of our prior knowledge, right? So we've captured all of our prior knowledge inside of the way that we've trained this exposure term. So now let's actually represent it down into equations, right? Now, why do we not start directly with writing down all the equations? Well, because that can have cursor dimensionality. You can have there's exponentially many ways or combinatorially be many ways. You can write down, these high dimensional functions, right? But in this form, we can do the training process where we've taken into account everything that we know, all of our prior knowledge. Once we've found this neural network, we can start to poke at it and just say, what did it actually learn? And here what we could see is that, I let this neural network be a function in this case of S, of I, and D. And one of the interesting things is it comes out and it says, well, the best fitting function here is a function of S and I, and you leave D out. Which makes sense because for COVID-19, exposure to the disease was not dependent on the number of people who've died. People who have died, they did have the disease, but they are no longer infecting individuals or no longer exposing them, right? And so this is something that you can directly read out from the sparse identification. Now, again, the interesting thing here is that because there is so much mathematical model around the object, you can actually interpret it, right? Because it's now there is a lot of there is model around it. It's not a completely amorphous object. It is a amorphous black box within a interpretable piece. So as you start to learn more information about that black box, you start to and how it interacts with the rest of the model, then you are starting to learn what you did not know how to model, right? And so this piece of information, like, oh, D is this exposure is not a function of D. This is a type of a type of scientific hypothesis, right? Now the reason why I think that this is interesting is because it allows for scientists in the loop, right? We're not just doing this in like a purely trust the machine learning has learned something. You can actually get some information out to then be able to go back to the lab and say it's made a prediction about what needs to be true for this exposure term to be acting the way it is. Let's actually go double check this, right? Now the other thing that happens here is that you actually have some improved generalizability. So we kind of see across the board that when you do the sparsification process, you do tend to improve the generalizability over just having the pure neural network. And there's a lot of reasons for that. Kind of comes down to some of the properties of extrapolation of polynomials. And if anyone wants to ask, it's something that we haven't been able to prove, but we have some good ideas of the direction for for what to do there. So yeah, so someone asked a question here. So say the neural network is convolutional with arbitrary channels and feeds. How to best combine T and X in this case? I will go into some uses of convnets or in convolution operators for PDEs a bit later. So I'll go back to that. For the COVID prediction example, how do you determine the functional form of the internal sparse regression? Yeah, so we have to make we have to choose a for example a library of functions that we want to do the sparse regression to. It could be things like every combination of polynomials, cosines, trigonometric functions, exponentials, and earth, like so you do have to make a choice there about how expansive you want that dictionary to be, and then you simplify it down. But in general, I mean that's one of the algorithms involved here. I could go into more detail, but it's really one step of the process, and it is a modeler choice at that aspect. Yeah. Now, one of the things I want to kind of highlight here, about when I start with scientific machine learning, I say, well, it's you're pouring in model, you're pouring in data, and your goal is to, if you have enough prior knowledge, if you have enough knowledge, right, where knowledge can come from data or it can come from models, as long as you put enough knowledge in, you should be able to get a good prediction, right? You just need to be able to hit the prerequisite amount of knowledge, right? Now, one of the things that we've done, why I like to start with this epidemic model, is because we had a lot of papers and such with Sandia National Labs where we dug into that idea, where we said, okay, this is a choice, right? It's a choice to say it's only one term. I could have made two terms. I could have made this entire part of the equation neural network. There's a continuum of how much model you have and how much data you're relying on, right? And so one of the questions that we asked is, as you go through this continuum of more to less model, does it actually work as we expect, right? Does it actually work like this figure, right? Where the more model you dump in, the less data you need. Or another way to put that then is, if you have more prior model and that prior model is correct, will the universal differential equation be able to give you better predictions from the same amount of data, right? That's another way of stating that same sentence. And we have some work with Sandia, which, kind of goes over a whole load of cases in different epidemic models with simulated data and all these cases to really show that property tends to hold, right? So you can kind of think that, this is something across the board where, with these universal differential equations, it's not a question of like how many data points you need, right? A lot of these things we're doing it with 20 data points or 40 data points, right? So it is a lot less data than something like a standard deep learning framework. But the real question, the real answer at the end of the day is the more prior model that you have and the more correct that is, the less data that you need. And so it is really, it is really not an you cannot say you need 30 data points, because whether you need 30 data points is dependent on how much other model you've put in there, right? So I would say go check out some of this work. And I forgot to put in here the work with Sandia that really highlights this aspect that really just shows the whole continuum of models and just shows how adding different parts of the model into it then incrementally improves that extrapolation performance. So but I mean, that's in the general idea here, right? The more prior model that you have, the more prior knowledge that you have, the better it will end up predicting. Now, one of the things that we've seen with the universal differential equation stuff is kind of explode in terms of how the number of people really using it in practice. So I like to highlight this work of some folks that we actually have this now inside of our SciML documentation, and it's one of our tutorial examples where what they did was they took these readings of gravitational waves. This is the LIGO gravitational wave data from the binary black hole experiment that first found the gravitational waves, right? And what they say is they go, well, gravitational waves, they come from black holes. Black holes are big, and so they're not well defined by Newtonian physics, right? But what if we assume that we only know Newtonian physics, right? Which is the equations that they have here, and we augment the Newtonian physics with these neural networks to learn what the relativistic corrections would be. Can we learn what the relativistic corrections to the motion of two-body large objects directly from data, right? And what they show is just that from a small amount of data, right? So just this small amount from the time series here, they're able to learn how to augment the Newtonian mechanics with a correction, and that correction then adequately extrapolates for being able to predict the motion of the two-body problem. It changes it from being elliptoid, which is the Newtonian solution, to a Lysygy pattern. And so if you're interested, I could pull up the documentation example of doing this. It's kind of at this point it's just like a nice reproducible example that we use to teach students about how to do this process. But it really shows the scientific machine learning in action. But I mean, there's a lot of examples that do this. So for example, here's a case with earthquake safe buildings where the original model, if you look closely at your screen, you'll see these dotted lines where the original physical model, it could fit, but it wouldn't necessarily extrapolate well. But after doing the training, after doing the fitting, again, improves extrapolation performance. And then the interesting thing from that, though, is that not that it's improving the extrapolation performance, but but what you can gain from this process is that it's told you how your original model was incorrect, which tells you the things that you did not know before that would be useful to know about in order to do better engineering. In this case, they wanted to engineer earthquake safe buildings. And so this told them what correction needs to be done to the model in order to then understand how to build a more earthquake safe building, right? Again, there's two things to this. There's the extrapolation accuracy aspect, but also the fact that it's improving what you know about the model that you're trying to build. And I think that second aspect is probably even more important. Everyone likes to think about, line goes, low cost with machine learning, but I think that improving the way that people build models, improving the speed at which people get accurate models, that is probably the more important aspect here. Now, I can go through like 50 billion more examples of where people have used UDEs, but I've already done a talk directly on that. So if you want more proof points on it, I'd say go check out this talk on YouTube. It goes into a lot of interesting examples as well. I'm going to cut it here and say, there's a lot of other examples that we can show, but now so knowing that people, what the general idea is, and how and the fact that scientists and engineers are using this in practice, what I want to kind of go into more detail here in a mathematical way is what are the other things that you can do beyond the basics of it, right? So that I really was just showing the basics, but what are some things that you can do to get creative with the UDE formalism, right? And I think that I really want to kind of show is that the formalism really allows for generally imposing prior known structure. So what do I mean by that? So so here's a case that comes from that same epidemic line of work that we're talking about, where I said you have this continuum of models, right? So here's something that lives in this continuum of models where you might not know that much prior information, but but you can impose a lot of the detail. So here, for example, let's say we wanted to model something like the SIRD case, right? So susceptible becomes infected, infected either recovers or dies, right? So what you can do in this case is, you can walk into a new situation, and as a modeler, you can very easily know, like, oh, people who are susceptible become infected, and infected people recover or they die. That's not a very strong assumption, right? But it is. It is. I mean, it's a graphical relationship, right? It's basically saying susceptible people do not recover without getting infected first, right? So can you encode that graphical information into a machine learning structure so that way that is prior known information, right? The UDE formalism is very flexible, right? It's just you put universal function approximators in differential equations in smart ways. So here, for example, is a way to do this, right? So you can have a neural network SI, right? So we have 3 neural networks. So here's one function approximator. So we say there's some function I don't know, where you subtract it here and you add it here. There's another function I don't know, which is you subtract it here and you add it back here. Then there's a third one, right? So there's 3 functions I don't know, but these are the places where these 3 functions go. And by design, what needs to be true about this then is, well, again, there's a lot of properties that I've just imposed here. For example, the number of individuals the number of susceptible individuals is always decreasing. You're going to have a peak in I, right? There's a lot of properties about an epidemic that I've already imposed directly only from this information. There's no prior equations really written down, just structure written down, right? And so what we're able to show from this is that you can then do the training of the neural networks in this case, right? You train the neural networks, and then you do the sparse identification of the dynamics. And you're able to then recover what the exact equations were, right? So we can simulate data, we generate the data, we then fit back to it, and then we see that we can directly predict what these equations are. But importantly, what we can show is that you can do this, you can accurately recover the equations using this form with less data points and with less data points than what would be required than directly doing something like the direct Cindy, like the Stephen Brunton sparse identification approach, right? So because why is that the case? Well, because we've imposed prior information here, and so we've really brought down the structure that we need to learn, and so from the same amount of data or from less data, we're then able to recover the same equations, right? And so this starts to show you that you can start to get very crafty with the types of ways that you're putting together function approximators and using any drop of prior information that you have. So another example that came up, which recently was actually published into Journal of Chemical Engineering, if I remember correctly, is a case where we have this chemical reactor and we're running a chemical component over it. So there is one chemical that is flowing with an advection diffusion process, and then there's another chemical which is non-spatial, so it's just an ODE process, and they're interacting, right? We don't know what this interaction is, so what we do is we model that interaction within function with a neural network, but we know a lot about the rest of the process. It's a reaction diffusion partial differential equation coupling an ODE with a PDE term, right? And now one of the interesting things about this formalism is by design now, right, I only have to learn an R2 to R2 function in order to actually learn everything I did not know about this model, right? So I have spatiotemporal data. Like, if you think about it in the sense, I have spatiotemporal data, and from spatiotemporal data, I have n by n, times t time points, but at every single time point, the same exact chemical reaction equation should be occurring. And so what I want to learn is I just want to learn what that chemical reaction is. And so even with a small amount of data, so even with a small amount of time series, that is still enough information to be able to recover what the chemical reaction term is. And once I've learned what the chemical reaction term is, I can extrapolate into the future and get things correct, because the important property was whether I had learned the rest of the equation in order to accurately model the whole process, right? So, thinking about it like this, if you think about it as though it's a time series problem, right? If you just say learn from this time series how to predict in the future, machine learning is never going to learn what how to make that the red dots go through the red line, right? Or the red line go through the red dots. It just doesn't, the blue, the training data that we give it is insufficient for being able to do that, right? It's just not going, you could look at the picture and you can see, okay, machine learning cannot learn things that it's never seen before, right? But there is something that hasn't seen before. It's this prior information of, well, we have all this reaction diffusion equations and everything written down. And so by virtue of writing down the partial differential equation form, we've actually transformed a problem of learning a spatiotemporal process, right? Something that is, learning how to output things that are, n by n, to learning just an R2 to R2 function that is a part of a spatial temporal process. And we can then, under many assumptions about, the fact that this reaction is independent, the reaction constants are independent of the time and location where it takes place, right? That is encoded by writing it down as a semi-linear partial differential equation. So by writing it into this form, we've encoded a lot of prior knowledge that has made it a fairly easy learning problem that then makes it so that way from small amounts of data we can extrapolate. And so, you might ask the question of, well, what happens in this case when we do the sparse identification? This one was actually a fairly interesting one for doing this identification, because, after we do this process, we fit the neural networks, the student went in and did the identification process and saw that there are a lot of cases where the equations were not exactly the same as, when you do this in the case of generated data, you generate the data with a known equation for these reaction terms. And then you go and you say, I'm going to run this process. I'm going to find out what equations I get. And you see that the equations are different, and the student was not happy that it turned out like that. But then we dug into it, right? We dug into it a bit. What we noticed was that if you actually do a second order Taylor series expansion of the different terms, what you see is that these equations are lining up, right? So it's what this really means then is that the sparse identification is not necessarily able to tell you exactly the equations that generated your data, right? Because it's kind of ill-posed, right? That's not, you need infinite data to be able to really fully identify the function. But what it can show you is it can show you a simple function which is locally able to match the right properties of the true function, right? So here, when we do the second order Taylor series expansion, the two functions are pretty much directly with each other, right? And so there's a lot of properties you can get then, right? So from the learned kinetics, for someone who's looking at reaction equations, right? You can say, well, if I have a q, if I have a q squared term, this is a self-interaction kind of reaction kind of term, whereas a QQ star term, well, this is a interaction between them. In some of these cases, the chemicals were non-interacting, right? And so there's a lot of different information that you can pull between these pieces just by learning the equations, even if they're not exactly the same form that you started with. It is a form that is representable, interpretable, and usable for doing the scientific process, right? And so Oh, I do like to highlight that this is a kind of nice case where we were using scientific machine learning in an industrial setting. So we were working with a Formula One team. This was the Williams Formula One team, where originally they used a Gaussian process model. So this is the original Gaussian process model for being able to model their speed over ground sensors. So the speed over ground sensors, as they drove around a test track, they would get this data that would basically tell you the orientation of the car, but that needs to be calibrated using the GPS data from the test track, right? And so what you can see here is the calibrated prediction of the car's orientation from that speed over ground sensor. And the original model did not take into account a lot of the physics of the car, right? It would basically just say, here's my sensor data, and here then is the prediction of what the orientation would be. And you can see it has a lot of these, effects, which, it's similar to the hallucinations that ChatGPT does, which is effectively, it's giving you things that are non-physical, right? The car is not actually moving like this, right? The car's true orientation is the color underneath, and you can see that a lot of a standard machine learning model does not necessarily need to satisfy physics, right? It does not necessarily need to satisfy the fact that your car cannot just bounce around infinitely fast, right? But what we were able to do is we were able to put a very simple model of the car's vehicle dynamics and say, well, what we don't actually know in this process is the relationship between the sensor to the vehicle dynamics. And so by putting it into that form, a form in terms of differential equations, which naturally would be integrated, that naturally then smoothed the process and incorporated prior knowledge about, the relationship between angular momentum and velocity and these features. And that made it fairly easy to be able to get a much more accurate prediction from the same amount of data. So, one other thing to kind of then highlight here is that, so what is this UDE formalism? Well, this UDE formalism, another nice piece about it is that you can rephrase a lot of other SciML methods as UDEs, which makes it a very nice form, as someone who writes computational software, to kind of formalize around. So here, for example, is a nice example of this. So there's work done by Han Jensen and N1 A, which is on methods for very high dimensional semi-linear parabolic partial differential equations. And they had this method where they talked about how you can solve these PDEs by using neural networks embedded within backwards stochastic differential equations. I'll skip over the exact details of this whole process, but essentially this is one of these scientific machine learning methods for solving a PDE using neural networks in a specific way. And they came up with this formalism where they'd say, you build this recurrent neural network, you train it with respect to a given cost function, and then you'll have something that will be predicting your PDE solution, right? Now, the reason why I want to skip over it is because, when you start to talk about things and work with things in this UDE formalism, there is actually a fairly nice way of writing down what their algorithm is. Their algorithm is a universal differential equation, which is written as this SDE, where there is this function that it goes right here that is unknown. And when you learn this neural network and a neural network that predicts the initial condition, you satisfy a loss function on the initial condition. So you solve this stochastic differential equation in reverse, and you learn how to predict that initial point. Then you have the neural networks that give you the solution to the PDE, right? So you can go and you can show then in a lot of different cases that a lot of ways that people have been looking at using neural networks and mixing it with scientific practice. The general formalism of it is as a universal differential equation, right? So this version of saying, oh, I have this recurrent neural network that was written down is simply the Euler-Maruyama discretization of this stochastic differential equation, right? And so, if you want to then, generalize their work, one of the ways you can generalize their work is just discretize this SDE using, adaptive methods or higher order methods or, all these different types of approaches, right? So understanding what the continuum continuous object that is giving us, when you do this in the UD formalism, you can write down the continuous object for which the discretizations give you these resnets and RNNs and things that are then used in a lot of scientific cases. But you can then start to see that those are special cases of a more general object that you can then, do a lot of nice, mathematics more simply on. And so, we've been building out packages for doing a lot of these different type of scientific machine learning techniques, which really then just uses everything in the UDE formalism. And so, the core of the software is do UDEs well, and then all these other cases are just, well, this is this ODE with this discretization, etc. And so it makes it very easy for us to be able to repurpose the same underlying training architecture to many different problems. I think that's just one thing to highlight as to, we think about this UDE formalism, one, as a way to impose prior knowledge, but secondly, as a computational tool, similar to like an ODE solver or a, Newton's method, right? It's a way to be able to turn the scientific machine learning into a computational tool that is then repeatable to a lot of other applications. Now, I want to get back to then the story of differentiable simulation, right? That's where I started with, and so I haven't talked about differentiating simulations at all yet. And so, why does this require differentiating a simulator? And well, the thing is, I haven't told you anything about how I train these neural networks yet, right? So, how do I actually train a neural network in one of these cases? Let me show you an example. This in an example. So here is a case where we're looking at surrogates of climate models, right? So this is a three-dimensional Boston-esque approximated Navier-Stokes equation, and what we want to do is we want to learn from the three-dimensional PDE how to approximate its dynamics in the z direction, right? Just the height column. We just want to turn blocks of ocean into just one-dimensional PDEs. Now, you cannot do that exactly because, well, Navier-Stokes has curl involved. You cannot represent curl in one dimension. But what you can do is you can, approximate it by, you can take the average, if you take the original Boston-esque equations, you take an integral average along these slices here, you can get an approximating PDE, but that approximating PDE is missing a term, which then requires you to have another PDE, which has another PDE, etc. Right? So this is one of these closure relationships that I'm sure a lot of people are well aware of. But instead of saying, oh, here's a term that I need to compute from another PDE, which is missing a term that's computed from another PDE, what I do is I just scrap all the extra terms and I just say, here's a term that would be computed somewhere else, but let me learn what that term is, right? So if I did not have the neural network, this is called the standard convective adjustment parameterization to the ocean model. But now what I'm doing is I'm saying, well, the convective adjustment equation is missing extra terms. Let me capture that with a neural network. Let me capture the closure terms with a neural network, right? So here, this is just the setup for my test case here. And now how do you actually train this neural network, right? Well, you can go back to your data and you can say, well, here I have data that, I get the average temperatures. I can take the slice, the green slice, the red slice. I can take slices on the z-axis to be able to know what this average temperature, capital T, is. I can do dt by taking finite differences between my data points, right? I can ddz. I can calculate this operator by finite differences. So you can go to your data and you can do all this differencing. And if you do all that differencing, you can calculate what is del t, and what is the right hand side actually. And then the neural network needs to be the residual between what the data is giving you and what the rest of this calculation would have given you without the neural network, right? So what I'm saying here is that you can directly go to your data, apply all the derivative operators, and then learn and build a data set that is then the neural network should take in this value and it should spit out this value as the residual, right? You build up that data set, you put it into PyTorch or TensorFlow, you just train your neural network, and then after you've trained the neural network, you stick it into your simulation to correct your simulation, and then you run it. Right. And so what we did this process, and we see that this did not give as good results as any of the other things that we've done with scientific machine learning so far. Right. In fact, it has a very specific behavior to it. So as you run the simulation more and more, you tend to get a drift that is accruing more and more error as the time goes on. So why would this be the case? Well, one way to understand what's going on here is that what we've done is we've came up with a process for this neural network must be, my derivative is incorrect. So this neural network must correct my derivative or control my derivative. Now, if you're a controls engineer, and you hear that term, that we're only applying control to a neural network control to our derivative, and then we are getting a drift term, it should be immediately apparent that one of the things that we're missing is something like an integral term that pulls us that makes sure that we don't have this drift, right? Now, another way of thinking about this is the process of munging your data set to be able to get a data set to train the neural network has nothing to do with the simulation process. Yet the simulation process itself is imposing errors on the process. And so if you build your loss function and train your neural network and then stick it in your simulator, you're not accounting for all of the properties that your simulation process will also impose. And so therefore you're training your neural network without all of the information that it needed to be the correct correction, right? Either way you thinking about it, you end up in the same point where the right thing to do is, instead of training on the derivative data directly, what you want to do is you want to directly use the temperature data, right? This average temperature data, write a loss function down where you solve your model with the neural network embedded with it, and you check whether it's hitting the right temperature values. If not, you gradient descent and you change your neural network until it is, right? So instead of training on the derivative terms, you're training on the integral of the neural network inside of your model. And what happens when you do this difference is you get about 2 to 3 orders of magnitude better performance and better fits. Right. And so, the other way to understand this, of course, is that, your simulation process is imposing its own errors, its discretization errors, and all these properties. And this training process is actually using the simulator as part of the loss function definition and making sure that it's correcting for that. So that way, when you actually do the fit, you're getting something that is correcting for any of these other errors that you've imposed in that simulation process. Right. Now, either way, we've now ended up in this formalism where we say, well, fitting neural networks on data outside of simulators and then sticking them into your simulators, right, does not give as good results as fitting neural networks as part of the simulation process. But how do you fit things as part of the simulation process? Well, then that means you have to have your loss function be something that solves the PDE defined by the neural network as part of it. And what you have to do then is you have to take whenever you want to take the gradient descent step, you have to take the derivative of the solution of the PDE with respect to the neural network parameters. And this is that differentiable simulation aspect. And so how do you actually do that process? Well, we say the adjoint method, but the adjoint method is actually there is a lot more than just one adjoint method. And it's, so let me describe this in one way. So the best way to describe that there's more than one adjoint method is to show you that you cannot just use one choice, one popular choice for all problems, right? So here, for example, the neural ordinary differential equations paper describes one adjoint method, which is if you have an ODE, u prime equals f of ut, sorry, that z should be u. You solve this ODE going forwards, and it says if you solve this ODE, then you can solve this ODE in reverse, and then magically it will give this last term, or this term right here gives you the derivative of your neural network with respect to parameters, right? And all it does is it relies on this numerical or this mathematical property that if you solve an ODE going forwards, u prime equals f going forwards, then solving u prime equals minus f in reverse should put you back in the same place, right? So that's a property that is true mathematically. But if you actually look at real equations, that doesn't necessarily numerically work out. So for example, here if we look at the advection equation, if you discretize the advection equation, remember you have to choose a way to discretize, either using the forward point or the reverse point, upwinding or downwinding. And so if your wave, if this PDE is describing a wave that's moving to the right, you're either choosing, that your next value to the right is using your information from the right or information from the left. It should be obvious that if you don't ever use the point from the left to update the point to the right, it does not actually have the actual solution for this motion, and so one of these is unconditionally unstable. Now, the issue with using an adjoint method as described like this is it says, well, if you solve the ODE going forwards, now we're going to use as part of our adjoint approach that if you solve the ODE going backwards with u prime equals minus f, you will, you use that as part of this adjoint derivation. The issue with that, when you apply it to something like this partial differential equation, is that that is not true for this PDE, right? So if you solve this PDE, right? So if we discretize this PDE into a set of ODEs, say the upwinding equation, you solve it going forwards, right? If you reverse the process, u prime equals minus f, when you reverse this process, the reverse solve will be downwinding, and therefore you will have chosen the wrong direction and get unconditional instability, right? And so what this really highlights then is that there isn't really just one adjoint method, right? So this paper talks about here is a way to differentiate ODE solutions which has O of 1 memory. It turns out that it has O of 1 memory, but it has the downside that it is not stiffly accurate. So it's not accurate on stiff equations, and it is and it's not able to handle cases like the advection equation, right? So instead, what you need to think about with this, with differentiating, these differential equation solvers and other equation solvers, is that the adjoint methods and the way of calculating derivatives, they are approximating equations themselves, and so they have numerical properties. And so similar to how with an ODE solver, you have to choose, do I have a non-stiff or a stiff ODE? And yet these methods have different properties. They have different, scaling properties and different stability. Similarly, you have when you start looking at the derivative approaches, the ways to calculate derivatives of these differential equations, you also have changes in the properties where there are some methods which are stable but require more memory. There's some methods that are stable and require more compute, and there are methods that are unstable but use less memory and less compute. And so you have this engineering trade-off between the different ways and the different methods for differentiating systems. And you don't just have a trade-off in terms of stability. You also can show that some of these methods have scaling, which is cubic with respect to parameters, which can be fixed by doing all sorts of different tricks. So this is the paper Stiff Neural Ordinary Differential Equations that goes into a lot of detail in the differentiation process. But the key that I want to highlight there is that, when you just say use the adjoint method, that's like saying eat an apple, right? It's like, okay, a Gala apple, or a Granny Smith, or a pink lady apple, right? It's there are many it's like saying solve an ODE with an ODE solver. There's a whole world of different methods there, and they actually each of these ways of doing the derivative process, it really imparts different numerical properties and different stability properties and all these different things that come into play. So when actually doing the UDE formalism, the difficulty and the interesting part is all in the part that I leave out of the talks, which is the how do you do it stably? It's all in the mathematics of the derivative calculations. But the key then is that you can do the UDE approach on any kind of simulation process that you can differentiate. So this is what we've been building out as the Julia SciML ecosystem, which is doing things like linear solves, nonlinear solves, right? If you could if your model is to write an actual integral, well, you can mix that integral function with neural networks, or you can write down an optimization with neural networks, a PDE with neural networks, right? In all of the different cases where you can write down a mathematical object where you knew the function, you can extend this to the case where you have a neural network, as long as you can differentiate adequately with respect to that process. And so what we've done with the Julia ecosystem is we made it so that with the whole ecosystem of equation solvers all connect with the machine learning tools, so that way you can do this universal universal approximator mixed in modeling approach to be able to generalize any type of scientific modeling to a scientific modeling that is augmented with neural networks. And I want to skip ahead here to just one beat. So for example, we've been using this a lot with Moderna, but I'll skip over with that, and the story with chaos. I want to kind of get to this this last story of very quickly, can we generalize beyond ODEs and PDEs, right? So everyone talks about ODEs and PDEs. what can we do beyond that? Well, it turns out that the way to start understanding things beyond just ODEs is to look at chaotic systems. Chaotic systems actually don't differentiate correctly with automatic differentiation. I'd be happy to elaborate on that in detail. But it turns out that what you can do, though, is you can define new forms of derivatives and new forms of adjoints, which are, while the derivative of the solution is not really well defined of a chaotic system, the derivative of ergodic properties with respect to parameters is well defined, and you can start to do things like fit fit ODEs on time point values that are more than a Lyapunov coefficient away, using average properties of the system. And so so this then kind of gives you a generalization of the UD formalism to this case where you have a lot of randomness, pseudo randomness due to the chaotic nature of some of these processes and the error imparted by them. Now, one of the other interesting cases then is, can you do this in cases like discrete jump models, right, where derivatives are not normally defined? So what we've done is, if in this something that was recently shown at NeurIPS, was that in traditional differentiation, you take what you do is you take your equation and you try to find a derivative. But in the generalized sense, what you can do is, if you have any kind of random variable, you can try to find a new random variable whose expected value is the derivative of the expected value of your original one, right? So what you could do is you could say, I have some series that does some stochastic process, and what I want to do is I want to find a new stochastic process whose expectation acts like the derivative of my original process. And if you can do that, which I'm running out of time here, so I'm not going to go over the whole thing, but the idea behind it is, instead of looking at small perturbations, like small perturbations, what you do is you look at small probabilities of having an O of 1 change. And when you do that kind of approach, you can start to build out these systems where, if you were to have, say, an agent-based model, you can directly run automatic differentiation on that and get the derivative of the expectation of your agent-based model. So if you have an agent-based model, you can run a process that generates a new agent-based model for you, where when you solve this new agent-based model, the expectation of that agent-based model is the derivative of the expectation with respect to parameters of your original model, right? So it's like some new model, it's a pseudo model, but when you run this pseudo model, it gives you the derivative with respect to expectations of your original model. And so therefore you can use it to be able to, say, train neural networks, so that way your original agent-based model is learning the functions that would define the rate parameters of your model. And we're able to show this then in cases like extending, for example, Conway's game, stochastic version of Conway's game of life, to something where we're then able to fit the parameters inside of there and be able to start mixing that with neural networks, right? So instead of just looking at this world of, we have ODEs and PDEs, you can start to say, well, we have all sorts of different scientific models. We have agent-based models, we have jump processes, Gillespie processes, and all these things. And in any case where we don't know functions, we can replace functions that we don't know with neural networks. And as long as we can find adequate ways to be able to differentiate with respect to the weights of those neural networks, we can then learn what these functions are inside of this process, and then use that to be able to identify the pieces of the model that we didn't know. And it gives us a direct generalization of scientific machine learning to that domain. And I think I'm about at time there, so I'll skip right there to questions. I see that I do have one question here. So in the Navier-Stokes 1D model, what's the input for the neural network term? Does it only take one grid point local? Or yeah, so for that, for this case, we actually looked at a bit at doing this in a way that is local and non-local. It turns out that there is some mathematics behind this process where it says that the operator in general here should actually be non-local in order to be correct. So we made this so that with a neural network actually takes in the full vector of the average temperatures. And we had another case where it was only local. So making it local is actually equivalent to making this be acting as a convolution network. And that did not actually perform as well, which matches up with a lot of the theory then about it being, about the closure term being a non-local operator. Yeah, good question.
Yeah, thanks, Chris, for the talk.